Before we discuss the area of a graph, there's just one thing that I'd like you to remember. If you recall the last class, our graph was this, or it was this, or say it was this. In all these graphs, we find that this one is a positive change, this is no change, this is still a positive change, which is not of course constant because the slope is changing. So if you are going up the graph, you are going uphill. But also remember that there are graphs which go like this. What does this represent is that as your x increases, your y is decreasing. So when you go along the graph, you are not going up, but you are coming down. So in this case, the slope of this graph will be y2 minus y1 upon x2 minus x1. So if you see here, this is x1, so correspondingly the y1 is here. The other one is x2 and y2 is here. So if you see here that this y2 is actually less than y1, therefore the slope will be negative. Therefore, this kind of a graph has got a negative slope. So if you know that when you are doing experiments, say in later on, and you know, as you increase something, something is decreasing, then you will get a graph like this, and the slope will be negative. So this is something that you need to keep in mind. Now today, of course, we are going to do the area of a graph. This area of a graph is relevant only for a velocity time graph. So let's draw the graph for a body moving with constant velocity. So let's say this is the graph because the velocity v1 does not change with time, therefore the velocity is constant. Now if you see, this is the origin. So for the interval of time t1, the graph will give you this shape, and the area of the graph is going to be the area of the shaded figure, which is nothing but a rectangle. So the area is length into breadth. So the length is t1 and the breadth is v1. But if you remember that the velocity times the time, that is velocity multiplied by the time, is nothing but the displacement. So this is something that we have an important result, and that is the area of a velocity time graph will give us the displacement. Say you've got a graph in which you are plotting force with displacement. So if a constant force is producing a displacement, in this case, once again, the area of the graph is the area of this rectangle whose length is s and whose breadth is f, which is f into s, a more familiar form. So what we have there is that the area of a force displacement graph is force multiplied by displacement, but which is actually the work done. So this is, you can say, some of the important significances of the area of a graph. And now let's utilize this information, that the area of a velocity time graph gives the displacement and the slope of a velocity time graph gives us the acceleration, to derive some equations of motion. Say we have time on the x-axis, and on the y-axis we have velocity. So this is velocity. So we take a general case of a body moving with a certain initial velocity u. I say a general case because u could even be 0, in which case your graph would start from here. But let's say it's starting from here. And then its velocity becomes v after time t. So this is time. So it's a simple graph. The initial velocity is u and the final velocity after time t is v, and the fact that this is a straight line shows that the rate of increase of velocity is constant. That means acceleration is uniform. So this is the equation of motion that we derive for uniform acceleration. Now if you look at the graph, so let's say this is A and B, because the slope of AB will give us the acceleration. Now if you recall, this is, so how do we get the slope? From here to here is V, and from here to here is U. Therefore this one is V minus U, and from here to here is T. So your acceleration is the vertical height divided by the horizontal distance. So V equal to U plus A T. This is one thing. So this is our first equation of motion that we derived by taking into account the slope of this graph AB. So when we calculate the slope as the vertical height divided by the horizontal distance, we get V equal to U plus AT. Now let's try to calculate the area of this graph. What is the area of this graph is this shaded figure. That means this figure in blue. So the total area of this figure will give us the displacement or the distance traveled by the body in time t. Now area is the displacement. Now if you recall here, this is a trapezium, so the area is half into the sum of the two parallel sides. So from here to here is u plus from here to here is v, and this is time is t. So this is an important expression that you need to remember. And if you see here, which I will write as u plus v upon 2 into t, this is nothing but my average velocity. So displacement is average velocity into time. Now coming back to this equation, if you see here in this one, s is half u. Now instead of v, I will write u plus at from here. So u plus at into t. So I've got half 2u plus at into t, which when you open the bracket, you will get ut plus half at squared. This is our second equation of motion. Once again, you go back to half u plus v into t, this equation that we got from the area of the graph. And then we recall v is u plus at. So v minus u upon a is t, which I want to now replace here. So I've got half v plus u plus v can be written as v plus u. This is v minus u upon a. So you have v square minus u square upon 2a, or v square is u square plus 2as. So we've got the three equation of motion. V equal to u plus at from the slope, then s equal to ut plus half at square from the area, and s equal to rather v square equal to u square plus 2as also from these two. So this is how you derive the equation of motion using your velocity time graph. If you recall the question, it says a car travels with a uniform velocity of 25 meters per second for 5 seconds. So let's see if we can convey that information now. So this is our velocity and this is our time. So the question says car travels with a uniform velocity of 25 meters per second for 5 seconds. So this is the part that represents car traveling with uniform velocity of 25 meters per second for 5 seconds. And then it says the car is uniformly retarded. So uniformly retarded means the velocity is now decreasing at a constant rate, so that I can draw a straight line, so that finally it comes to rest. And it says in further 10 seconds, that means this should be 15. So for the first 5 seconds it traveled with a constant velocity of 25. Then in further 10 seconds it decelerated uniformly to finally come to rest. Now the question they are asking is, find the distance which the car travels before the brakes are applied. So if you see, the distance which the car travels before the brakes are applied is this one. That is this part of the graph where the speed is constant. So this one. It is only here in the 5th second the brakes are applied and then the car decelerates uniformly and comes to rest. So in our case, the distance traveled before the brakes are applied is nothing but the area of this blue rectangle, which is length into breadth, which is 125 meters. Now then it says I need to find the retardation. So for the retardation, this is the retardation. So PQ is the retardation. So if you see, the slope is the retardation. So slope is nothing but the vertical height divided by the vertical height, this one, divided by the horizontal distance. So now keeping in mind the slope is such that when I am going down the slope, I am going downhill. I put a negative sign here. So my vertical height is 25 and my horizontal distance here is 10. So that is minus 2.5 meters per second square is your retardation. And then finally, we need to calculate the distance traveled by the body after the brakes are applied, which is now the area of this figure, which is now, if you see, it's a triangle. So the area is now half into base, which is from here to here, which is 10, into height, which is 25. So 125 meters. So we have this, that in the first instance when it was traveling with constant velocity for 5 seconds, this is the distance traveled is 125 meters. Then the brakes are applied and the car decelerates uniformly to come to rest. So the deceleration has been calculated as minus 2.5, which is the slope. Why minus? Because the velocity is decreasing, we are going downhill. And finally, the distance traveled in the deceleration is the area of this triangle, which is 125. So if you were to find the total area, then it is simply 125 plus 125. If you recall our previous derivation, if you want to find the total distance traveled without breaking it up into these two parts, you could simply calculate the area of this one and this one together. Of course, it has been made simple so that we calculate it separately. In a real life situation, this could be, a car is traveling at a constant velocity and maybe he sees something and applies the brakes, but he takes some time to react. So this time that he is taking to react, in which the car is moving at the current speed, is what they call the thinking distance, and this is the distance that he moves when he puts on the brake and decelerates. So this is one example in which you have used a motion time graph to calculate in a very simple way a problem that involves acceleration and displacement.